this keyboard. Take the IFFR. So inverse Fourier transform, we're going to sound SC this. This is your sound SC demo. It normalizes it so that it doesn't exceed 1. And I'm doing this for reasons that are currently unknown to you. But you will see when we look at the signal. What do we expect to hear? You expect the same thing?
Well, you said phase doesn't matter.
Anyone hear anything?
Impulse? Really weird one.
A little bit.
Is it like a drone of everything at the same time?
Yeah.
Let's take a look at what it looks like. Plot. And remember, we expect the magnitude spectrum to be the same. Nothing has changed on the magnitude, but the phase has changed. So we're going to plot new y. Get it anywhere we can. You know what? I'm just gonna. I love having these backup things, so I don't have to type. We can listen to it again. So look at this thing. If you can't see it very well, we've got this huge impulse here. Why don't we make it so you can see it very well? You get a huge impulse, and then you've got all this stuff, and then you have a huge impulse.
Did you do the IFFT of the IFFT?
No,
Wait, what? Y is
New
IFFT.
I used the big one. Sorry, I should have kept it the same.
Yeah, I got you.
I figured I'd simplify that a little. So we've got an impulse, a lot of quiet stuff, which is actually the more interesting stuff in this case, and then another impulse. Anyone have some thoughts? What did we do? We didn't just strip off the phase, we made it 0. We didn't discard all, we did discard all phase information, but we didn't take away the fact that these signals have phase. We set the phases to 0. Next, we can randomize it and see what that does.
And negate it. Negate the untapped phase.
We can do that too.
Oh, with negating the unwrapped phase play in reverse?
But the phase is part of the complex amplitude, so you can't just like take it away, or you're kind of changing the.
I did just take it away.
Yeah, well you can, but like, you're changing the amplitude if you just discard the phase information, right?
Because they're all the whole.
Well, you're not changing the amplitude of each component.
Are we taking all the components of the signal and starting them at phase 0 and then just
Exactly.
run?
Exactly. What's a cosine equal to at phase 0? 1. So at time 0, all these things are overlapping and you're getting constructive interference.
I see.
So you get this huge impulse. And it actually, this impulse is the other side of this impulse. So they're the same thing. It's all just concentrated around 0 and it's periodic. And all the extra stuff is here.
And if you remove DC, those impulses should look identical.
If you remove DC, those impulses should look identical. I don't understand that.
Well, the impulse on the left is taller, right?
Yep.
That's because it's got DC. But then the very next bend has to be exactly the same as the first bend to the left, which is wrapped around, because it's symmetric. Because it's a sum of cosines. Cosine is symmetric about time 0.
Yes. Why does adding DC make it not symmetric?
Because there's only...
DC is adding the same thing to the whole signal.
Yeah, the time 0 sample is unique. It's just like DC is unique. So there's only one pileup at time 0. Time zero is here, and it would be right here. It'd be the very next sample.
Yeah, I understand that.
So that's why I'm saying at time 1, you should have exactly the same amplitude as time -1. And then at time 2, if the impulse is that wide, you would have that. I don't know. How
So you're
many
saying our
signals it is.
signal's symmetrical now?
It's symmetric
roughly.
at that time because it's a sum of cosines.
Mhm.
Exactly. But the DC makes the I call it DC is the time 0. It's the DC component of the spectrum. It's the time 0 component in the time domain.
So we're going to listen to this again, but we're going to cut out that nasty impulse. Because when you have the big impulse and you do sound SC, everything else gets really small. But when you get rid of that and you do sound SC, it rescales it and it's not small anymore.
So is it the same thing but adding like pi over 2? Or?
No, we're just clipping the signal so the impulse isn't there. We're taking 500 samples off the beginning and end.
That's cheating.
So you get to actually hear it. Well, it's not cheating. I mean, it's just listening. It's just listening to the signal.
It's like almost.
That actually sounds really cool.
Write that into your score, yeah.
I think that's a usable sound or something.
Yeah, and I mean, I did next to no work. This was really one important line of code here. And I could have done the FFT and the IFFT right in there.
So, and basically what I heard when we had just with the impulses still in, doing the whole thing, we're working with 8,000 samples, right?
Mm-hmm. Yeah,
So
roughly.
we're cutting off, so with the impulse there, what I was hearing in the quiet bit was sort of everything that was going at the first moment steadily over the whole thing. When we cut off 500, are we now hearing, because I was hearing.
It's the exact same sample.
Yeah.
You just get rid of the pop at the ends.
Okay, so we're not taking it from some, if we've got 8,000 samples and let's say the 30 seconds about that we listen to,
Mm-hmm.
taking 500 off the beginning and 500 off the end is not going to start it later and end it earlier?
It is. It's going to start it later and end it earlier in the stripped sound, the one with no phase information.
Yeah, so I guess
But what does that correspond to in the original? It's very ambiguous. It's
Okay,
messy.
Okay, I was just wondering why I was hearing things moving in that last one, or was that
Probably because the volume was louder. Because the relative.
The volume is louder. Really, all it changed was I got rid of the impulse so the volume would be louder. Let's listen to it again. So if you listen, you can kind of hear the Alleluia in a bunch of different places. It's a weird thing, and I'm actually surprised that it's that apparent. Here you can kind of see that it's symmetrical. That's interesting.
It's similar to when you hear something through a shell.
Mhm.
You take a shell and the beat has all these spinnings inside. And if you were to hear something that is going into that shell, but only coming out of the shell without knowing what is inside. The phasing information is gonna get lost in the shell as it bounces in it. That's what I'm thinking of as an antenna node.
It's like a kind of reverberator.
Yeah. What would happen if instead of setting our new values to be only real, what if we set them to be, I don't know, J times absolute value?
Then
Would that
you're
just be equivalent to doing signs at the frequencies?
That'd get rid of the big impulses. Bring them down.
because that's kind of scrambling the phases in different ways, isn't it?
So instead of setting the phase to
90
0, we'd have
degrees.
like, I don't know, negative 90 degrees or 90 degrees.
Let's do it.
Pi.
Easy enough.
Oh, and then if we got rid of the,
So your
we
signal,
didn't do the cutting off of the samples at the end?
it still isn't.
Oh, so
So now your IFFT is no longer. Okay, what you'd really have to do is set the positive frequencies to plus J and the negative frequencies to minus J.
That would be nice. That would.
And I think we have time to do that. So let's do it in a loop because I don't want to think about how to do this without a loop. Let's steal the thing from over here where we only look at these So this is Chet waving his hands over MATLAB stuff. I love sheep. Okay, so we're looping over those, and if it's got a conjugate pair, we're going to do Y.
Who's going to the opera this Sunday to see Handel in San Francisco? Nobody? Am I the only one?
Sorry, buddy.
Oh, no.
I'm gonna be all alone.
Which opera?
Partenope? Is that how you say in English? Partenope? That's how we say it in Spanish. Partenope. Like this, today.
Well, it's a real signal.
That's weird, I mean, it's distorted, there's something distorting it.
Yeah, I don't
All
know.
you did was say, what did you do there?
You randomized the phase?
No, I just added a phase shift to each of them. So they're all at 90 degrees, and I did it symmetrically.
Mhm.
They're all at 90 degrees.
Yeah. So I made the negative frequencies have negative J phase shift, and the positive frequencies have positive J phase shift, and the reason I did that is just so it's still conjugate symmetrical.
But you will expect still the signal to sound better than that.
It sounded pretty distorted. I don't have a reason why.
Did
Are
you
you
have
sure you're not
sound
changing the
SC?
magnitudes?
Yeah, it's scaled.
Am I sure I'm not changing the magnitudes? Positive, because I'm doing that. Oh, wait.
Oh.
New Y.
New Y.
Haha.
Why would I have expected it to be any different?
There's a lot more high frequency stuff going on
Man,
here.
it sounds like staticky AM radio.
Yeah, where's the static coming from?
I don't know where the static's coming from. I don't have a good reason for that.
Okay, random.
Rand, and it wants something that's the right size. Oh, sorry, the sampling rate is 8,000. The length of the signal is not 8,000, it's 73,000. Rand is 73, 3113, 1. We can flip it if it doesn't work. Let's flip it. This is how you learn to MATLAB. Maybe it wasn't the flip, it was the dot. It was the dot. That damn dot. How fun.
Is it possible that if you increase the sampling rate, it's going to sound better?
Well, I mean, there's not increasing the sampling rate on this thing isn't going to do anything. If you upsample it and fix the things associated with upsampling so that you have a higher frequency and the same higher sampling rate and the same sound, it'll sound the same because the upper bandwidth was lost when you sampled this. If you just upsample it without doing any filtering, don't worry about filtering and upsampling yet. It'll sound faster and it'll sound crappy, but
Hey, how about
actually
changing-
upsample drops it, but
How about changing that second abs to real? Second one, not that one.
here?
The next one, abs, yeah, instead of taking the absolute value, that will cause distortion, whereas the real part will give kind of a linear projection onto the real axis, so to speak. So now we're distorted, and I think that if we mess with it, it'll remain undistorted.
Times angle.
So remind me what we're doing again. Are we taking the FFT of the entire signal or just the beginning?
The whole thing.
The whole signal.
Adding up.
The whole thing all at once? I mean, okay. Did we already reproduce the signal correctly?
I didn't show that because it's not very interesting. But if you just do FFT inside of an IFFT, you get the same thing back.
Okay.
We did it for the other signal.
Yeah, we did it for that other signal. I just. Are you convinced me? Yeah.
Okay, that's So in a non-obvious way, we're getting the same thing back. We're taking the absolute value and doing this, which is multiplying it by the right phase. This is just stripping it and putting it back together for no apparent reason.
Yeah, try that.
Aren't you glad we're doing handle now?
A little backwards. Yeah, that's
Did you just
You-
reverse it by?
Yeah, you flip the phase, it reverses it in time.
That's awesome.
So let's make it a 2, because why not? That's So giving it any random number is more or less equivalent to scrambling the phases, because when you change the phase, it changes it by a different amount of time for each frequency. So, what is the difference between this and your homework example where changing the phase didn't matter?
What is the difference you say?
Mm-hmm.
The way that-
We had a periodic signal before, and now we have.
Bingo. No phases. Time reversed.
So this illustrates the proverb, phase was invented to keep everything from happening at once.
Who said that?
Julius.
Julius. Probably was. In the beginning, there was only Julius.
Julius to MATLAB.
So, what happens when we combine that previous program and this program? It's thinking. This is a long sample, and it's dumb, and I didn't code very efficiently. It's busy. Okay, so rather than do this sample by bin by bin, I did it in chunks of 5. So it's doing 1/5 of the spectrum. So all we're going to hear is the black stuff. Low pass.
Okay, this brings me to something that I mentioned that I'm in an fMRI class, and we are talking about phases there. And this reminds me of that, because they limit the parts of the signal that they are actually imaging
Mm-hmm.
by doing a Fourier transform, and then taking only the center or the outer limits of the signal components.
That'll give you the high frequencies?
Yes.
Yeah.
And this is, they talk about it as the K space, but I don't know if this is the same.
It's a spatial frequency.
Yeah, but that's like 2D, and this is only one.
Yeah,
one thing.
but it corresponds to exactly the same thing. A lot of the stuff from audio signal processing you can take over to the image world with very few modifications.
It's amazingly simple, it's just a double sum. So we sum over n, so if you go to the spatial xy plane, you have a sum over x, and you have a sum over y, and they're just nested. And the generalized sinusoid just becomes e to the j omega x plus y. I mean, it's just really, really simple. It's the same thing.
So let's give it.
Get a matrix for your FFT instead of y, right?
Yes.
Like,
Yes.
yeah.
Yeah, you get a two-dimensional Fourier transform, and DC is in the center, and things tend to go down, like a hill from there.
We could maybe do something like that one day. I had a nice program that would do a live FFT of your webcam, which is fun to hold up like little paper with a grid on it or dots.
And you can compute it. You can compute it by taking the FFT of every row of your image, and then going through and taking the FFT of every column of your image. So it's actually that simple to do.
It's also like.
So we
What?
heard how phase shifts are affecting the signal,
Mm-hmm.
but on the actual plot, we should expect to be seeing the same thing all the time, right?
Plotting magnitude.
Here I'm just plotting magnitude.
So on this plot, but
Yeah, I'm not doing anything funny with the phases. I'm just only playing the sinusoids that are represented by the bins that are in black. So the phases are remaining the same.
But,
All
when,
right, yeah.
but when we were playing with the phases, that plot didn't change either.
Yeah.
Yeah, the magnitude plot.
That's what I meant.
Yeah.
Not this one, the
Right.
previous one.
The magnitude plot has not changed for anything that we've done today. Only the phase plot. Get a little bit more. Let me finish this and then we'll do that because it's easier to hear these. Get a little more. Got a nice resonance there. I told you you would love this. The picture's a little behind.
Let's get some more low frequencies there.
This is a simulation of having wax for
Every time.
This is the last one.
Can you do it the other way around?
What, only do the high frequencies? Yeah, we'll do that one in a second. Azim?
You can remove the middle too.
Show us where in the code you split up the bins and played them separately. You said you combined the first part into the second part.
Gives it a real beat, you know? Recording's terrible. Sorry.
Okay. Yeah, I mean, you're totally cool to discuss this. If you want to discuss this, please do. So there was the question, can I see the part of the code that does this in groups of 5? Here it is. It just mods the number of things. There's a factor of 2 picked up somewhere. I didn't look into it. I didn't really care. So it's only doing any of the plotting and sounding if the bin that we're looking at is equal to an even multiple of 10. So I stuck a floor in there too, and the reason I did that is because if n isn't divisible by 2, you get a weird thing, and then non-integer indices, for those who care. We're doing it backwards now. I think. I don't know. We'll find out. It didn't do anything. Why didn't it do anything? Is there some reason? Oh, yeah, -1. Wait for it. Oh. I believe that's your Nyquist or something like that.
Something really nice.
Yeah, I didn't actually expect that.
No, you can hear the Sopranos though.
If your Sopranos sound like that,
That's like Mariah Carey's whistle register. It's my favorite lady piece.
Ross loves it.
Does that actually sound suspiciously like tenors?
We have a comedian, ladies and gentlemen. There's the good stuff.
Now it sounds like a Hallmark card.
Now it sounds like a Hallmark card. Because you're losing the upper frequencies, not because of this filtering, but because it's sampled at 8,000 hertz.
Yes.
And you're losing the low frequencies because I told them to leave. And you don't get to hear the original, I guess.
Oh, yeah, because he also starts
male
out
overtone.
I'm going to stick this back at 1. So I did some stuff today. Hope that was amusing. What questions do you have?
The only part I didn't quite understand was the last demo, where you're adding these only certain bins, right, to the original signal.
Yeah, instead of doing every single bin at once and listening to it, which would take the rest of our natural lives, I just took chunks of, n over 5 bins, or n over 10 bins, I guess. Oh yeah, I'm going through only half the frequencies. That's why that factor of 10 turns into a 5. But I'm doing them in big chunks rather than listening to one. You could listen to one at a time and you'd slowly hear it. But I mean, perceptually, would you pick up on one frequency being added? Probably not.
And why does that translate to being a filter?
Because when you filter something, if you've got some spectrum looking here only at the positive frequencies and it looks like that, and you pass it through some filter that does this, basically what you get is, this. This is your magnitude plot. It takes the high frequencies out. That's one of the main things we're going to use filters for, is to remove certain frequency ranges.
Right, but over here you're saying I want to take every 5 bins, right?
No, I'm not taking every 5 bins. I'm taking chunks that are so large that there's only 5 of them in the entire spectrum. I'm dividing the spectrum into 5 and just bringing back one section of those bins at a time.
Okay.
So I'm doing exactly what the picture showed. I'm only playing those frequencies.
Okay, can you just walk me through the code where it does that?
So it's executing this loop just as it normally does. So everything is really the same. The only thing that's different is I only plot it and play it if the index is divisible by the number of bins over 10. Is that clear?
So then it would just be the last and the first. Well, okay, so explain that.
So if I have 100 bins
Yeah.
and I want it to play only every 10 times, I do 100 mod 10. If that's equal to 0, I know that it's divisible by 10, because what's 100? This isn't quite what I want. I have your k mod 10, if that's equal to 0. And there's 100 bins, and k is going from 0 to n, or n over 2. It really doesn't make a difference.
So every 10 is going to be 0.
Every 10, it's going to be 0. So those are the only ones it computes, but it's calculating all the ones in between anyhow. So it only shows up every time that. Not something really to get caught up on. I can talk about it more if you're still not on board.
How is that equal to taking only certain bins, like the first?
I'm adding sinusoids back one at a time. I only stop and listen to it when I've added like n over 10.
Okay.
So I'm doing the same thing. I'm just not observing it as often.
Just listening to it at different points during the reconstruction process.
Exactly. Thank you. That's a good way to put that. Questions, Ron?
So what we've seen in these figures are plots of the DFT?
Yeah, your spectrum.
How will a plot of the inverse DFT look like?
It'll look, you mean if you only have certain frequencies?
No, I'm just trying to make sense of what.
If you take a DFT and then do an inverse DFT, you get the signal back.
Oh, okay.
If you take a DFT, only add up some of the sinusoids, and take the inverse DFT, you'll get a similar signal, but none of the high frequencies are there. So this is like a little window into filtering, no pun intended. But you don't have to worry about the filtering yet. This is just kind of, this is what filtering sounds like.
Yeah, we haven't defined filtering, and we'll get to it next, well, we'll actually talk about it next week, but if you take the FFT and modify the amplitude of any of the bins, that's a filtering operation.
Filtering should be clear to you on the level of, like, you walk into a recording studio and then you say, oh, that's great, but the high frequencies sound bad. Can you turn them down? Can you cut the highs? Can you give it a low pass filter?
So what you were doing.
Beyond that, I don't expect you to understand anything yet.
Right. You're just changing the gain at various frequencies.
That. But in this case, I'm making that gain 0 or not
Also
changing it at
delay,
all.
So it's gain and delay at each frequency, that's all there is to a filter.
What's that? Yeah, I'm just giving it a brick wall filter.
There's no like.
When I took an instrumentation class back in my undergrad, when we learned about the different partials that exist in a clarinet, for example, they introduced it as a way of filtering. But I think I see how it relates. But it's since I heard that, I thought maybe through filters you could make any signal sound like a clarinet, just based on the fact of what you have. But
That's hard.
You could,
theoretically, yes.
You can make like take the fundamental of the thing that you're, I don't know, like let's say you're singing, you could take the fundamental of your singing and then be like, oh, well the clarinet has these harmonics at
yes, if you can detect the pitch of your singing voice, you can run it through something like your additive function, and it's going to have to change over time to follow your voice or whatever, and add those harmonics in there, and you can have a clarinet that follows your voice.
Usually it's much better to use subtractive synthesis from white noise or that sort of stuff.
Probably.
It's easier.
Probably. I don't know.
The possibilities are endless. That is definitely true.
If you want to talk about that someday, throw together a presentation. I think it'd be cool. If you want to talk about that in class someday, throw together a presentation. I think it'd be cool.
Oh, geez.
If you don't, that's fine too. No pressure. I mean, that's all I have for today. So if you don't have any more questions, you're free to go about your lives. The class is kind of over anyhow. But you're welcome to keep asking. You got to do the lab. Oh, I know Halloween night is tomorrow. If you guys want to turn it in like Saturday, Sunday, that's fine. I don't really care.
But
Do you
include
care?
Candy for Chet.
Oh.
I will eat. I will eat candy, but I don't need candy. You don't care, do you?
No, that's fine. Yeah, no, I would do the same thing. It's hard to get your lab done when the doorbell's ringing every 2 seconds.
Or when you know everyone else is having fun. So if
Or
you
when
want to
you're
have
wearing
fun
your
on
hat.
Halloween, have fun on Halloween.
Wearing a big moose head.
You can trash in your non-running computer.
It's hard to do
The
in a mask.
lab today was awesome. Like all of the demos really made sense, and I think
Wonderful.
Yeah,
That makes
things
me
make,
happy to
like,
hear that.
0 sense to me in terms of, oh, so you have these frequencies, but what in the hell does a phase actually mean?
Yeah.
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 That
Like, I
conceptually
even have
made no
experience
sense until
and
today.
phase made more sense in this demo than it has in the past.
Yeah, for sure.
Goody.
Yeah.
I like this. This is good.
Yeah.
Well, I can come up with another demo for next week. I'd say 1 demo a week is about as much as I can reasonably prepare. I don't quite know what we'll do next week, but I'll come up with something.
As I was looking through number 8, actually before class, I just thought that as we watched these demos, I thought it would be nice if we could, when you take the phase into consideration, there will be a way that you could include a C plot into these demos, so that we see how phase is moving from the real to the imaginary.
I don't fully understand.
So, for instance, in the last question, in number 8.
Oh, you mean what happens to the phase plot as the phase changes?
Yes.
It's just going to shift up and down
Okay.
because you're adding that thing in the exponent. When you write your frequencies, You-
moving around the circle.
you have some phase plot and you're just adding a constant offset to it.
Oh, I had a MATLAB question.
Sure.
So I was playing around with MATLAB while working on number 8 for the theory. How do you prevent MATLAB from taking the angle of noise? So, like, you take the DFT of something and you know, oh crap, that sine wave should fall exactly into these 2 bins, but you know, you might get some almost 0 but not quite number, and then it's taking
In other bins?
the angle, yeah, in the other bins that you expect to be 0. It then takes the angle of it and you're like, oh, but that also should be 0 because I expect amplitude is
Well,
0.
things that are not quite, if it doesn't fall into a DFT bin, things that are not quite 0 are not
Yeah,
quite
but
0
in
for
the
a
case
reason.
Of, you know, the sinusoid that was your input signal should fall equally.
Oh, are you just talking about numerical noise?
Yeah,
So it's
if I
like
take
10 to the 13th down or more than that.
Yeah, but if you take, I don't know, the angle of like random number that's like basically, I don't know, 10 to the negative 13th with another number that's almost 10 to the negative 13th, but they're not the same value, you'll get some really weird angle.
Yeah.
But you
You're,
expect it to be 0.
you're dealing
How do
with-
you avoid that in math?
you're dealing with numerical precision. So you're trying to look at the phase plot of your FFT when it's just a sinusoid?
Yeah,
Only,
so I was expecting like, oh, okay, cool, so there's 16 bins and it's just one constant tone, so there should be a negative frequency with value 8 and then a positive frequency with value 8.
I mean, realistically, you'll probably only want to look at your phase at that frequency and just discard the rest as noise. I don't know if you have anything
That's a
more.
really good thing to do. Sometimes you can also like just add a small number to the real part of the spectrum, and then that'll give you, 0 whenever it falls down below that. So machine epsilon is, I think usually MATLAB has EPS defined, EPS, that tells you what your machine epsilon is. So if you add 10 times EPS to the real part, then it would hopefully go basically to 0 of the noise segments. It's kind of a fudge. I think Chet's answer is better, but you can do that just to clean things up without having to think about it.
Yeah, because I initially just looked at angle and I'm like, whoa, why are there all these weird values? And then I looked at amplitude and saw that it was 0.000, but then if it's,
Yeah.
10 to the negative 13th, it's just truncated. And you're like, oh, so it's
the phase of
Machine
quantization noise.
So yeah, one of the things that I wanted to make clear today is that you may not be able to do anything interesting with your phase information. You might look at that and say, great, I don't know what to do with this. That doesn't mean it's useless. You need it to reconstruct your signal. It may be very hard to interpret. It may not be useful to interpret it,
It encodes the timing of the information.
but you need it.
And since it's a sampled signal, that's why that matters.
Because it's
To reconstruct it. Because we're expecting continuous signals.
I mean, if it was a continuous time thing, it's the same story.
Yeah.
I think it's worth mentioning though. that
Harder to prove. You can't represent it on your computer. Sorry.
If we were taking small windows of the signal, only 20 milliseconds long, then phase doesn't matter for any kind of tonal signal. That's where the ear is phase deaf or steady state timbre. So if you take small chunks of the signal where there's only one vowel going on at a time, like ah in hallelujah or a in alleluia, if you've got that captured under a window, then the phase of that really does not matter. You can't hear any change as you scramble the phase. That would have been a nice addition. Yeah, maybe we could add that to the demo. So if you take a little small section in time, then we can show the phase doesn't matter. Whether you flip it, scramble it, whatever you want to do. It always sounds the same. So the ear is phase deaf on that time scale.
I guess I thought that, or I was interpreting the, when we first generated the plot with the two big impulses on the ends.
Mm-hmm.
I guess I'd interpreted that as basically that very small time slice, just in a steady state until the last impulse.
It was the whole thing.
It was the whole. Okay.
Yeah, so it had the ah and it had the lay and the luya. And what I do not understand myself is why does it sound mostly like ah
Yeah.
with little loos coming in every now and then?
The amount of that ah, those
I would say there's just
partials.
probably more ah.
Hallelujah.
So
You
that's
know, it's like-
dominant.
Yeah, the ah takes up like 2/3 of just the
Yeah.
time, and so that the frequencies associated with the ah partials are going to be more present.
They're dominating, but why aren't they always dominating? Why do I hear loo coming through?
It is very weird.
Yeah.
You do hear the
Yeah.
little bits.
I don't understand that, and it's at a low frequency. There's a low frequency ebb and flow of the loo coming in.
Yeah.
And I don't see it.
So is it more of like a magnitude thing? Like somehow like Lou is being stressed because Lou is like this musically the secondary focus of that.
Mm-hmm.
Well, yeah. Why is there the low frequency component? Why does it come in and out as opposed to just always hearing mostly ah? And
Well,
then
if
you pay
it's a
attention, you
low
hear the loo.
That's the question. And the answer has to be in the magnitude spectrum
Yeah.
somehow, right? Because we zeroed out the phase. But something about that magnitude spectrum
You
creates
could
a sum of cosines that looks like that.
you could still get like some weird beating between low frequencies, but I don't think those
That's-
frequencies are low enough that that's the issue.
I'd like to look at the timing of the loo coming in and see if that's like the first bend frequency. You know, could it be an artifact due to the sampling of the spectrum like that? You have to kind of do detective work of that nature
Yeah.
for these things.
Okay, so if
Very steady.
if this problem is something you're really interested in, I'll wait till he's done.
Yeah, that'd be another test.
If this problem is something that you're really interested in, take this code and change the bounds of the array, or of the loop, the bounds of the loop. You might have to modify some other stuff. I'm not saying it's completely plug and play. And listen to only the peaks in the spectrum, maybe. Change the frequencies that get added back in. You should have a pretty clear idea of how the code works based on today, and you'll have it in front of you if you don't. Listen to those peaks. See, maybe they sound like ah, maybe they sound like yeah, or whatever. I think that would be informative. Listen to them on the zero phase, listen to them without. If you find something interesting, let me know.
Yeah, and if you figure out the answer to this puzzle, please share.